So looking at two molecules which are similar in structure and trying to utilize proton NMR to distinguish the two molecules, because if we tried infrared spectroscopy with the same functional groups, carbonyls and ether links, we'd get a very similar spectroscopy printout for these two compounds. Likewise, with the mass spectroscopy, we'd get a picture which will look very similar. Chemical formula is the same, so the molecular ion peak would be the same. There'd be a couple of minor changes on how the molecule fragments down and at which points, but that isn't a subtle thing to look for. The most obvious differences would be in the proton NMR. So if we take a look at our two molecules and take a look at the hydrogens which are next to the most polarized groups. So for example, if we look at these two comparative carbon positions, A and A dash, looking at carbons which are next to ether links in the two respective molecules, we would expect the peaks to appear round about the same area in both molecules. Of course, that would be a range of somewhere between 3.3 to 4.5, but the number of hydrogens producing those peaks and the splitting patterns would be unique. For example, on compound on the left, carbon A here, there aren't any neighbouring hydrogens because of the ether link, and so those three hydrogens would be a singlet in that 3.3 to 4.5 range, compared to the second molecule, which has just two hydrogens at this point next to the ether link. And because these two hydrogens do have three non-equivalent neighbours, that signal would be split into a quartet compared to just a singlet for the first compound. If we look at the other major polar covalent group, the carbonyl group, on the two molecules and their neighbouring hydrogens, we'll call them B and B dash. We get on the first molecule on the left for B, we've got two hydrogens which have three non-equivalent neighbours, so that would produce a quartet in that region, 2.0 to 2.4 for the peak. However, with our second molecule, we don't have any neighbouring hydrogens, so it would be just a singlet, and it would also be for a different number of hydrogens, that peak, 3 hydrogens compared to 2, and a singlet compared to a quartet. So that's usually the best way to compare the two molecules. Look for peaks which should be appearing in the same region, and look at the integration, the number of hydrogens producing that peak, and also for the splitting pattern. And this would be two peaks that we could look out for, which would easily distinguish between the two molecules.